Hello and welcome back to another part of the easy speedrun, and the problems for this set are going to be on trees. So if you have some issues with trees, this is going to be a great one for you. So let's get started. Given the root of a binary tree and your target sum, return true if the root has a root to leaf path. Okay. Okay, root to leaf. So we're gonna. Okay. So we need to think what we are returning here actually. I think the way to do this, the better way to do this would be, yeah, so we're going to traverse down this tree and we're going to give it a target, and then when the target is 0, I think that's what we're going to return. That's going to be the easiest way to do that. So we're just going to have some kind of like res equals false for now. Then we're going to make a helper function, node target. Then if not node, return target equals 0, because that would be true. We don't actually want to return. No, this is fine. Okay, so otherwise, yeah. Actually, we don't want to return. We want to return 0. Yeah. So otherwise, or actually, we don't even need to do this. No, actually, let's do that. So then left equals helper node dot left target minus node dot val. Then right equals helper node dot right target minus node dot val. Okay, now what we want to say is we want to say, yeah, if node.val equals target and there are no children, then return true. So yeah. So do we need these left and right, by the way? I don't think we need them. Yeah, I don't think we need them, so we don't need to record. So if target equals node.val. Actually, we don't even need to. Yeah. Okay, so we can do a couple things here. So if target is node.val, so I think these are all positive. No, they're not. Okay, so we do need to go all the way down. Okay. So if target equals node.val and not node.left and not node.right, then we can update this res, right? So res. And then what are we actually returning here? We don't need to return anything. So actually what we do need to do is we do need to call these. Actually, we could just return here, so let's do that. If target is node.val, and we could return right away here. But actually it doesn't matter because this is a leaf node, so it doesn't matter. Node.left target minus node.val. Okay, I think that should be it. So we're just checking every single node. And if not node, return 0. And we don't even need to return a value, we just return. Okay, and then now, so let's just call that. I think that works. Target sum, return res. Root. Okay. Alright, merge two binary trees. Imagine when you put one of them to cover the other, some nodes. Okay, so we're just going to be making new nodes here, so this is pretty straightforward. Yes. Okay, so what we need to do is we just need another helper function, and then we're going to say root, just call it something else, right? So root A maybe, root B. Okay, so if one of these exists and the other one doesn't, then what do? We need to make a tree node. Yeah, okay. So if root A and not root B then we need to make a tree node here. So node equals tree node. And that's going to be root a.val. Okay. And then we need to do something else, but that's fine. Okay, so let's just do node.left equals helper. So let's do the one case if they're none of them are true. So if not root A and not root B, then we just return none. Okay, there we go. So if root A and not root B, root left helper. So there is no, so root A dot left none. Okay. Then the other case is L if root B and not root A. Right, same thing. So node equals tree node root B dot val node dot. So we do need to do a left and a right. So A dot right none. Okay, root B dot val node dot left equals helper. So not root A, so none here, and then root B dot left. Node dot right equals helper. None root B dot right. And then the other case is if they both exist. So this would be else. So we'll just copy this code. And it says you need to merge. If they overlap, then sum them up. Okay. Otherwise, the not null. Okay, so this is just going to be root b dot val plus root a dot val. And that's going to be root a dot left, root a dot left. Am I doing something wrong? Oh, this is right. Right. Let me just return the node. So return node. Then we need to do return. So we're just making a new tree, basically, of root 1, 2. Can't say we screwed anything up. Looks like we did. So let's take a look at this, if we can, possibly. Okay, 1, 2, 3, and what are we getting? Okay, so we're getting these two different nodes. Okay, and so what's our output here? So what should our output here? So our output should be 1 and then 2, 3 on both sides. What are we getting? Run. 2, 2, 2, 3. So it's close, okay? So we probably just screwed up one of these, so let's just double check here. So if root A and not root B, node equals right, left, oh right, it's the usual. So okay. Alright, next one. Convert sorted array to binary search tree. Okay, so what we need for this is we need a left and a right pointer, and we're just gonna take the middle as the root. So left right equals 0, length nums. Okay, nums length equals 1. Okay, so there you go. Now same thing. We can just do LR, so we use different variables. So if L is greater than or equal to R, that means we don't have anything, so return none. Otherwise, we're going to make a root. Yeah, so let's make a pivot first of all. So equals R left plus R. We need the center over 2. Okay, so we need to make a tree node here. So node equals tree node. That's going to be nums pivot. Yeah. Okay, and then now we just need to pass in the helper. So node.left equals helper. So left is going to be left pivot -1. Node.right is going to be helper pivot. Also, this is going to be +1, right, return node. Should be it, I think. So return helper. This should be left, right. We technically don't even need this, so we can just do this. We could do 0 length, but whatever. Because we're not using it anywhere. Okay. Okay, so we're screwing something up here. Interesting. So let's just see what this would look like. So we're 0 length num -1, that's fine. Okay, so if I think this shouldn't be equal, this should be only greater than r. Okay, there we go. Because if left is equal to r, we still have a root. Okay, same tree, given the roots. Okay, so this is pretty straightforward. We can call the function even here. So if not p and not q, return true. If q and not p, return false. If p and not q, return false. Okay, so that takes care of that. Now we just need to recursively call down. So they have to have the same value. So return p.val equals q.val and self. So we're just going to recursively call this function is same tree p.left p.right. Oh no, this is q.left. We're just going to recurse down and check the nodes. So and self dot is same tree, and this is p.right q.right. So we're just recursing down, and that should be it, I think. Okay. All right. Subtree of another tree. Given the roots. Okay, so this is pretty much this problem here, except we need to check the entire tree, and now this could be anywhere. So let's make a helper function that checks the trees, and I think this helper function is going to literally be some code like this. So let's just do that. So helper, and let's just say this is p, or we need to make it def, helper p q. Okay, so this is going to be the same code here, pretty much. And then, actually, it's going to be literally this for the p and the q case, except now this is going to be helper. So this is if you have two nodes. If you have two exact nodes, this is how you compare them. But now we also need to traverse down this tree and do any subroot, which would be, so let me see here. Can our tree be, or let's see here. If there's a subtree of root. Okay, so can our root or subtree be empty? No. Okay, good. So this is, we're just going to have a recursive case where we're going to recurse down this root and subroot. So return helper, right. Yeah, so I think all we need to do is we need to pass in root and subroot here. Root, or we can recurse down, right? So it's going to be self.is subtree root.left subroot, or self is subtree root.right subroot. Okay, yeah. So we're just gonna be traversing down this tree. That's what we did last time, and then this helper function is gonna compare every single node to the tree. Okay, let's see. All right. Okay, let's see what we got here. So none type. Okay, I see. Okay, so if it's none, yeah. So what we need to do is, if it's none, we need to. What do we need to do? Return false, I think. Yeah. So not root. Return false. So we Okay. Balanced binary tree. Height balanced. Okay, height balanced binary tree is a binary tree in which the depth of two subtrees of every node never differs by more than one. Okay. So I think what we can do is for every node we can get a left and a right, which would be just the maximum path length, and then we can check do those differ by more than one, and if they do, then we have an output. So like here, we would get this length, this path, which would be 0, let's say, or if we count the node, it would be 0, and then here it would be 2, and so there's a difference. So we would have res check or something equals, let's just make it true for now, and then we can update it later, and then we can have a helper function. So a helper node. So if not node, return. Okay, otherwise, so if not node, we're going to return 0 for the, right? Because if a node has no children, it's going to be 0. So then we need to do, so then we need to just get the left and the right path length, right? So let's do that. How would we do that? Okay. So I think what we want to do is we want to do left equals helper node.left, then right equals helper node.right. Okay. Now we want to say if, so we're gonna figure out how we get these values, but that's fine, and what we're going to be returning. So if absolute value of left minus right is greater than 1, that means it's not height balanced, then we're going to do non-local res equals false. Okay, now we need to figure out what we're actually returning here. So what we need to return is we need to return the node, I think, plus the maximum of the left and the right. Yeah, that makes sense. So like if we're here, maximum left and right is 0. If we're here, maximum left and right, yeah. Okay, so return 1 plus max left right. Then we just simply need to call our helper function on the root and return the check. Oh, what do we got? Oh, this is not res check. This is check. Okay. All right. Diameter. Return the length of the diameter. The diameter of a tree is the length of the longest path between any two nodes in a tree. The path may or not pass. Okay, so number of edges between them. 1, 2, 3, 4, 5, 3 is the path 4, 2, 1, 3. Okay, so the diameter, it looks like it's the longest path on the left plus the longest path on the right. So that's going to be kind of what we did last time, right? So, and then we're just going to keep an output variable called res, and we're going to make that 0 to start. And it doesn't have to pass through the root, but we're going to handle that. We're just going to take, at every node, we're going to take the left and the right, and then add those together, and that's the diameter, I believe, right? So, yeah, so 4, 2, 1, 3, we're not counting the actual root value. That's fine. Okay, so same thing. Okay, so if not node, we want to just return. Do we need to, yeah, so we do need to output something, so we do need to return 0. Then we're going to do this diameter thing. So left equals helper node.left, same thing. So you're going to see like a lot of these are the same patterns. If you're doing tree problems, you're going to be doing a lot of this kind of stuff. Node.right. Now we need to do this this diameter thing. So if left plus right, so we'll just add this non-local again. Okay, if left plus right is greater than res equals left plus right. Now we need to return, what do we need to return? We need to return, so if we're here, we need to return 1. If we're here, we need to return 2. Yeah, right, so we need to return 1 plus, same thing, 1 plus max left right. So this is literally the same problem as last time. Then we just need to call helper on the root and return res. Okay. Cool. All right. Maximum depth. Number of nodes along the longest path. Okay, and how do they? So this is pretty much the same as the other problem, actually, except now we just have to figure out that the nodes along the longest path counts the root. So the maximum depth, so for one thing, the longest path is always going to include the root, right? In any problem, like in any of these problems, the longest path is always going to have the root because everything goes up to the root. So what we can do is we don't need a res value here. We're just going to return it directly. So we're just going to same thing, def helper node if not node. Okay, return 0, and that's probably what it does. Okay, otherwise same thing, left equals helper node dot left, literally the same code. And so by the way, if you do want to practice, like I think when I'm doing these problems, a lot of these problems are the same data structure. So if you do want to practice one data structure, this would be good. Just take the 10 problems in what I'm doing and try to do those as fast as you can, or not even as fast as you can. Just try to do those, and then you're gonna get the easy stuff for a data structure down. Okay, so this is left, right. Then we are going to return. What do we need to return actually? The maximum depth, right? So, and we are going to include the node. So we're gonna return 1 plus, oh, this is literally the same code, I think. Right, so here the left would be 1, here would be 2, so it would be 3, yeah. So now we don't need a res value, we can just return directly. So it's like the same problem. Okay. Invert binary tree, the classic, famous invert binary tree, that's hard to do. Okay, so we're just swapping every node, so that's also straightforward. So def helper. Oh, it's node. So if not node, same thing, return. And this is usually in these recursive functions. When it's not, you just do that. Now you just do pretty simple. You just swap them and then you go down, right? So node dot left, node dot right equals swap them. Node dot left, then we just recurse down. I don't think we need to even return anything. Yeah, I think we just call it. So then return the root. Okay. Yep. Okay, post-order traversal. So we had the other traversal. So a post-order traversal is, let me get this right this time. Okay, so I believe it is a left-right root. Yeah, I think that sounds right. So same thing, helper node. And then we're gonna, oh, we also do need a array here, so. Okay, so same thing, if not node, return. Now we need to do left, right, root, right? So helper node dot left, helper node dot right. Then we need to append node dot val. Then we're done, so we just call it root return res. Okay. All right. Cool. Okay, let's go over these problems and do the complexities and see if we have any kind of stuff to think about. Let's have this here just in case. So path sum given the root of a binary tree, target sum. Okay, so this is pretty straightforward. So all we're doing for this is, like, let me show you. So let's say we have this this first example, right? So we have a 5, 8, 13, 4, 1, 4, 11, 7, 2, and our target is what is it here? It's 22. So all we're doing is starting with a root and we're passing in a target 22, and then whenever we're at a node, we just ask ourselves, is this node empty? And does the value equal the target? So here, obviously, it's not. So then we have to recurse down, right? So we're recursing to the left and the right, and we are subtracting the value of the node because that's the remainder that we need, right? So if we have a 5, we need 17 more. So we pass in 17 here, 17 here. Let's say we go to this left one first. Okay, obviously this is not what we need. So then we go down again. So then we pass in 13. And this is not what we need again. So then we subtract again. We pass in 2. And here we see 2 equals 2, and this has no children. So this is going to return So we don't even need to return. All we do is we just say if we did match what we need, we have this non-local res, and what non-local does is it lets you access a value that's a variable that's declared outside the function if you want to change it. And then we just make it true, and then we can finish. So that's all we're doing. And then if we never hit this case, then we're never gonna change this res value. Now let's do a time and space complexity for this while we're at it. So time, we're gonna traverse every single node, so that's O of n, because we're not stopping. Like a more efficient algorithm probably would stop once it gets to the right node. Okay, space would be O of n as well, because we're not guaranteed to be balanced. So this tree can just be like 5, 8, 4, 1, in which case we'd have to traverse the whole tree. Okay, let's take a look at this one. So this one's also pretty straightforward. All we're doing is we are passing in two roots. So let me draw this real quick now for this example. So let's say we have this 1, 3. Let's draw what this would look like for the output. 5, 2, 1, 3, 7, 4. Okay, so we pass in two roots, so we're here, and now every time we are at a new place, we're gonna make a new node, and that's gonna be our output. So let's say we're at these two roots, and then if one of these doesn't exist, then we just take the value of the other one. So in this case, they both exist, so we make a new node and we add up the value. Then we say, okay, the left is gonna be, we're gonna go left on both. So let's go left. So now we're here for both, and we do have a value again, so that's gonna be 4. Okay, now let's try going left again. So here we're going to go here, but here there is no value. So because there is a value here and there isn't a value here, we're just going to take this value here. So that's 5. Now we are going to recurse back to this node. Then we're going to try going right. So we're going to try going here. There's nothing, but there is a node here. So we're just going to take that node. Okay, now we recurse back up here, and then recurse back up to the root, and we do the right. So there is a node and there is a node, so we're going to add them together. Now we're going to try to go left. There isn't a node on either of them, so that we don't add anything. Now we're going to recurse back. We're going to try to go right. There isn't a node here, but there is a node here, so we're just going to take that node right there. And that should be the right output. So we're just basically traversing down both of these trees until we hit a spot that has them both being null, and then we can recurse back up. And if there's one, we take that one, and if there's not, we add them together. So pretty straightforward there. Okay, so this convert, so let's go over this one. So if you want a binary search tree, I think they want a height balanced one. And so what we can do is if we have this array, the best thing to do, so we have an array like this, -3. And I might do some problems later with these left and right pointers for making a tree, where you're going to have some array of like a sort of in order traversal of a tree and how to make a tree out of it. So if you want this to be balanced, well, what's the smartest spot to take a root, right? We're going to want to always take the middle. So what this left and right thing does is we have a left and a right pointer. So let's say in the beginning we have our left points here and our right points here. Okay? And all we're doing is at every single iteration we're taking the middle and we're making that a node. So the middle here would be this 0, right? So we're taking the 0, we make a node 0. Now we have to update it. So when we try to get the left, well, the left is going to be every node to the left of 0, right? So what we need to pass in is we need to pass in our left, and then our right needs to be updated to over here. So then so let's try to do that. So now our left is here and our right is here. And now we do the same thing. So we try to get a middle, and for this case, either one works. If it's two nodes, -10 or -3 works, but let's say we use -10. Okay, we use -10. Now, obviously we can't get a left, because when we try to get a left, our right is going to be over here, and then our left is going to be greater than the right, which would give you nothing. And this is how you check if you have no nodes. If the left is greater than the right, then you have no nodes. So then we also need this right node, right? So when we go to the right of this node, this left and this right will be equal, so this will be the only node. So then we go to the left here, and now we my mic cut out there. So now we go to the right here, and then we put in this node. So then we go all the way back, and let me just erase all this. We go all the way back to our root, right? So at our root, yeah. So at our root, the left was here, right? And this was our root. And now we need to do the same thing for the right side of the root. So when we take the right side of the root, we take this left and we move it over here. It's the node past. So now our left is here and our right is here. And this is we're over here. So now the same thing. Any one of these can be the root. Either one works. Let's say we take this 5. Now we update our left to be over here, right? Because we use the left, so now our left is over here. And then our only node left is 9, and we can put it either way in here or here. It doesn't matter. And so that's either one of these would be valid. You can have a 10 or whatever. Either one works. So like you can have a -3 here, you can have a -10. But for a longer one, the basic concept is you're always taking the middle of your left and a right to be the root node, and then you're just updating the left and the right, and you know you're done because your left and your right is past your left. Okay, so that's pretty straightforward. And there are a decent amount of algorithms for there's some algorithms like make a tree from a post-order traversal or pre-order traversal. So you could try that if you want some practice with that. That's a slightly harder problem. Okay, so the same tree is also really straightforward. So all we're doing is we are just comparing node by node. And so if both nodes don't exist, then our tree is equal, right? Because then they're both null. So let's just go through this example real quick. Like let's say we have something like this actually. Instead of doing that, let's say this is 1, 2, and this is 1, 2. Let's go through this example. So we are saying if one of the nodes exists and the other node doesn't exist, then clearly they're not equal, right? So we start here. If one of these nodes exists and the other one doesn't, clearly they're not equal. But if they do both exist, then we need to check, are the values the same? And then we need to recursively check the left and the right. So the values are the same. If they weren't, they wouldn't be the same. Now we recursively go left, and they are the same, and then we recursively go back and go right, and they are the same. So you would just keep recursing down, but let's say this node had something like this, it had a 3. When you recurse down here and this had nothing, then if this has a node and this doesn't, then you know it's not the same tree. So that's pretty straightforward. And then this subtree of another tree is pretty much the same as the same tree. So this part is the same tree, but all we're doing for this root and subroot is we are checking every single. So this code's a little bit different, but all we're doing is calling the helper function on every single root of the every single node of the root, right? So we check this with this, or here, let me draw that real quick. So let's say we have this. One, 2, and then our subroot is here. So we start at the root and we ask ourselves, is the tree rooted here the same as this? And so this helper function is pretty much the same tree copy pasted, right? Because if you start at the root, then this whole tree would have to be the same whole tree. And then if it's not, then this part just recurses down the entire root. So we're saying either the root has to be equal or the left side or the right side, any one of these. So let's say we recurse down here. Now we check this tree with this tree. Is that equal? Yeah, it is. So then we can return true. So any one of these has to be equal, either the root or the left or the right, and we keep traversing down. So if we ever get a node in this tree that we can do the same tree operation with this tree on the right, that means it's the same tree, or a subtree. Okay, balanced binary tree. So we are checking to see if it is height balanced. And so this is also really straightforward. All we're doing is we are going down the tree, and then our base case is if the root has no tree. Oh, actually, let me go back and do some complexity analysis, where I think we missed a couple. Yeah, so this merge trees, we are going to every single node of both trees. So that would be, let's say there's n nodes in the first one and m nodes in the second one, it would be n plus m. Because technically we can't have a bunch of nodes in one that are not in the other. So we would have to check every single node of both trees. And then space, same thing, n plus m, because we are creating a whole new binary tree. And the most nodes you can have is, you can just have, like let's say you had one tree like this. It would just keep going left a bunch, and then the other tree would keep going right or something. Then the nodes in this whole tree would be this plus this. They would share a root, but everything else would be new. Okay. Convert sorted array to binary tree. So that's pretty straightforward. So this is O of n, because we are going through every single element in the array. And then space is O of n as well, because we're making new nodes for every single element in the array. Same tree is, we have to check every single node, so it's O of n. And then space, we're not making anything new, so that's O of 1. Subtree of another tree is going to be a little bit more expensive, so we have to go down every single node, but then we also have to check if every single node is equal to the subtree. So that would actually be if n is how many nodes are in the left and m is how many nodes are in the right. I think that would be n by m, because at every single node you would have to check every single one of these. Okay, and then space wise would be O of 1, I think, or actually no, this is recursive, right? So recursively, what's the worst case that could happen? I think it would be something like n plus m, something around there. Actually, would it be n plus m? No, I think worst case it would be n. Yeah, the most we can ever recurse down is n. So this whole tree, because we are going to recurse down to some root or some node, but then that subsection we have to check for this. So that would be the worst case, is O of n, where n is this left big tree. Okay, so balanced binary tree, I think this is the one we were on now. Yeah. And so the base case, so let me show that real quick as well. 3, 9, 20, 15, 7. Okay, so all we're doing is our base case is if a node is empty, then we're going to return 0. So like for here, this left would be a 0, this right would be a 0. And all we're doing is we're checking, does the left and the right differ by more than 1? And if it does, then it's not balanced, because a height balanced tree, the leaf nodes differ by only 1. So like here, this would return 1, this would return 1. We check, is 1 equals 1? Yes. Then we also, whenever we return, we're going to return this 1. So we're going to turn 1 plus the max of the left and the right, right? Like for example, if this had a bunch of nodes, then what's the height of this whole thing? Well, it's the biggest, it's the longest branch. So we're always returning 1 plus the longest branch, and then we're always checking, are the left and the right more than 1 apart? If they are, then we're going to take this check variable and we're going to make it false. And so time complexity for that one is going to be O of n, because we have to check every node, space. We're not making anything new, so O of 1. Okay, diameter of a binary tree. So the longest path is pretty much kind of the same thing. We're getting the height of the left and the right children, and then we're just adding them together, right? So the longest path, including any node, is just the left plus the right. So here the left would be 2. If we're in this node, the left would be 2, and then the right would be 1. So it's 2 plus 1. So we're just going to every single node, and we are checking what's the left plus the right, and is that bigger than our current total. And so the time space complexity would be, we're checking every node, and O of 1 space, we're not making anything else. Maximum depth, pretty much the same thing, so I'm not even going to go over that. It's basically the same thing. You just have some variable that you check, and what's the longest, except you're not doing left plus right. You're just doing what's the longest, the left or the right here. So time O of n space. But the nice thing about these problems is they're kind of similar, so it gives you a lot of practice doing the same thing, and you kind of do these, and then you get really good at like these simple concepts. So for invert binary tree, you can see the picture. We just traverse down. So like we're at this node, we just swap this left and the right, and then we traverse down, right? So we take the left and we make it equal to the right, and we vice versa, which is this right here. We swap them, and then we keep traversing down. So you can draw that if you want. I guess I could draw that real quick for this example. So we're at 4. We swap the left and the right, right? So now this becomes 7, 2, and then this is still 6, 9, 1, 3. Then we traverse. So let's say we're here. We swap these two nodes. We go down to 7. We swap these two nodes. So then this becomes 9, 6. We traverse down these two nodes, there's nothing. Then we go down here, we swap these two nodes. And then this becomes 3, 1, and that's the answer. Okay, so that's that one. Time and space is the same as the other one. And most of these simple ones, the time and space is usually going to be n if you have to traverse every node, or if you're doing some kind of looking for a specific node in a binary tree, that's when it would be log n, because then you're not traversing down the whole tree. And binary tree post-order traversal is the same thing. We are just traversing down the entire tree. And if you count the output, then it's going to be O of n. But if you don't count the output in space complexity, then it's O of 1, depending on what you want there. Okay, so that's all the problems for this one, and I hope you liked this video, and if you did, like and subscribe, and I'll make another one soon. So see you in the next one.